Good morning everyone. My name is Deepak Yadav and today we are going to study some complex topic which is in our digital system design subject, that is binary codes. So, binary codes are of many types, like we are bifurcate binary codes in either weighted code or non-weighted code. Even some codes are alphanumerical code and error detecting and correcting code. So, one by one we study these codes, and one of the very important code in the binary codes is the binary coded decimal. So, we start with the binary coded decimal, and then one by one we can proceed with the different number of codes in this topic. So, first one is the this is the content of the today's lecture. First we study binary coded decimal, then addition of these BCD numbers, then other decimal codes like 2421 code, 8421 code, and etc. Then gray code is again one of the very important. It is a unit step code which is used for in different applications. ASCII characters codes, and error detecting and correcting codes. So, the first code is the binary coded decimal. The binary coded decimal is nothing but these code is the binary representation of the decimal number. And for representing up to 9 digit, we need at least 4 bit to represent the decimal number. So, each BCD code must contain at least 4 bits. As you can see over here, for code 0, we have 0000. For 1, we have 0001, 2, 0010, and up to 9, 1001. So, each decimal digit is represented in the form of binary number, as we can see over here. Now, how the decimal number is presented into the binary code or BCD code, as we can see over here, like we have a decimal number 185 base 10, and we want to convert it into the binary coded decimal. So, each bit like 5 is over here, it is represented as 0100, 4 bit binary equivalent of 5, and it is placed over here. For 8, it is 1, 0, 0 and 0 over here, and for 1 this is the code. Okay, so this is the binary coded decimal code of the decimal number 185, but it is different from the binary code. So, for the binary code we have to divide 185 divided by 2 each time, and we save the remainder, and in this way we can generate binary code. So, the BCD is very different from the binary representation of the decimal number. Now, we have some applications in which we need to add the binary BCD coded number, and where there are such certain rules which is used for adding the BCD numbers. Like if we take a two decimal number 4 and 5, and the sum of these two number is less than 9, like as we represent the BCD number 4 as 0100, decimal number 5 as BCD 0101, and if its sum is less than or equal to 9, the sum is, if it is less than or equal to 9, as we can see over here, the sum is 0, 1, 0, 1 plus 1, 0, carry 1 and 1. This is less than 9. In this case, there is no need to any correction. The result is correct, and it is a correct binary BCD representation of the addition. But when there is a case when the addition of the two number is greater than 9, when sum is greater than 9, in this case we need some correction in the BCD addition. So, first represent 4 as the BCD, 8 as BCD, and we sum up 0, 0, 1 and 1, and this is actually 12, which is invalid number in the BCD. There is no 12 digit in the BCD. So, for correcting it, we have to add binary 6 in the result. As we add this result and this binary 6 in the result, we have 0, 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, and there is one carry bit over here. Now, for the binary BCD representation of this addition, we must add 3 zeros in front of 1, so that it became a 4 bit for representing the BCD number, and this is the remaining 4 bit. So, we have 1 and 2, which is BCD, this is the BCD result of the addition, which is equivalent to the decimal addition. So in this way, for correcting when the sum is greater than 9, we have to correct it with the help of adding 6 in the results, and the result is now matched with the normal addition. Similarly, there is one another case in which the sum of the number is less than 9, but there is a carry. And there is a carry exists in the addition, like in this case, when 8 is added into the 9, we have representation of BCD representation of 8, we have BCD representation of 9, and when we add, we have 1, 0, 0, 1 plus 1, 0, and there is carry over here. So if there is carry, then again we have to add binary 6 in the number, so that the number is converted into the BCD equivalent. The result is converted into the BCD equivalent. So as we can see, this is only 1, which is less than 9, but still we have to add 6 because of this carry. Because of this carry generated. So as we add 6, we have 1, 1, 1, 0, and carry as it is. For representing into the BCD form, we have to add 3 zeros in front of this 1, and this is 1 bit of the BCD, this is second bit of the BCD, and it is equivalent to 1 and 7, and this is matched with our result 17. So in this way, we can perform the addition. We have 3 special cases: when sum is less than 9, there is no correction needed; when sum is greater than 9, but there is no carry, then we have to add 6, and when sum is again less than 9, but there is a carry, then again we have to add 6 in the result, so that the result is matched with the BCD representation. So in this way we can perform subtraction as well. In the same way we can perform the subtraction, but using the complement numbers. Either 1's or 2's complement is taken over the negative numbers, and then sum it. And if there is carry, then we have to add carry in the 10's complement, and the 9's complement we have to discard the carry. In the 9's complement we have to add the carry, and in the 10's complement we have to discard the carry. But if there is no carry, then the result is in complemented form. We have to convert into the complement number and represent minus sign over that number. Then other decimal code. This is the other decimal code that is used, which is 8421 code. 8421 code is nothing but it is the BCD codes only. So that is from 0 to 9, it is represented as BCD, as we can see in the previous slides. There is another code which is having weight 2421 code. So in 2421 code, again we have the 4-bit representation of the numbers, but the weight is represented by 2421. So in this case, if we want to like represent 5, so for representing 5, we have to take this 1, 0, 1, that is the weight. The weight of this one is 2, the weight of this one is 2, and weight of this one is 1. So the total sum is 2 plus 2 plus 1, that is equal to 5. So due to this fixed weight pattern in 2421, we have to represent 5 in this way. In the decimal or binary representation, they have another values, but in 2421 code, this is equal to 5. So in this way, the 2421 code, the weight is fixed for the each digit, so that we can generate the different number in this way. The another code which is very useful is Access 3 code. In Access 3 code, this is it is access in 3 with compared to the BCD number that is already exists. So for the Access 3 code of 0, first we have to get the BCD code of 0 and then add binary 3 in this, and the result is 0011. This is the 0 representation in Access 3 code of 0. So for the 0 decimal digit, we have Access 3 is equal to 0011. For 1, it is again Access 3, that is 4. For 2, this is 5, and for 9, this is 9 plus 3, 12. So this is the 12 representation. In Access 3, it is 9. So in this way, we can represent Access 3 code as well. There is one unique property of the Access3 code that these codes are reflecting codes. Like if we see the Access3 code of 0 and Access3 code of 9, we see there is a mirror reflection, that is all the zeros is converted into 1 and all the ones is converted into 0, as we can see over here. This property is known as reflection of the numbers, of the binary numbers. So as we can see over here, the binary code of Access3 code of 0 and Access3 code of 9 is the mirror reflection of each other. In the similar way, Access3 code of 1 and 8 are mirror reflection. As you can see over here, this 0 is converted into 1, this 1 is converted into 0, and these two zeros are converted into 1. In the same way, this is the reflection of this code, this is the reflection of this, and this is the reflection of this. So that's why in the many application, Access3 codes are very useful for representing the number, where we need reflections of the number in the application. So this is again a very important code known as Access3 code. The another decimal codes are 8, 4, minus 2, minus 1 code. Again 8, 4, minus 2, minus 1 is the weight of the number. Like if we have a number 1, 0, 1, 1 in 8, 4, minus 2, minus 1 code. So this bit having weight 8, this bit having weight 4, this bit having weight minus 2, this is having weight minus 1. So if we want to represent what is the value of this number in 8, 4, minus 2, minus 1 code, this is 8 plus we have 0 in place of 4, nothing, then minus 2 and then minus 1, and that is equal to 8 minus 2, 6 and 1, 5. So this is the 5 representation of 5 representation in 8, 4, minus 2, minus 1 code. It is represented by 1, 0 and 1, 1. So in this way, 0 is represented as all the bits are 0. So for the 0, for 1, 4, then there is no 1 bit. So you can add, you can generate 1 as 4 minus 2 minus 1, that is 4 minus 2 minus 1, and it is equivalent to 3 only. So you can, so it is equivalent to 1 only. So this is the representation of 1 in 8, 4, minus 2, minus 1 code. Similarly for the 2, 3, 4 and up to 9, you can represent 8, 4, minus 2, minus 1 code. This is some unused bit pattern which is not used in these kind of code. Like in binary, we cannot use 1010 pattern, 1011 pattern. Similarly, in 2421 code, we do not use these patterns. In Access3, we do not use this because never 000 is never exist in Access3 because it is always excess of 3. So 0, 1 and 2 never use in Access3 code. Similarly, in these codes, these patterns are never used. So this is the unused combination used in which is not used in different decimal codes, as you can see over here. Now the another important code is gray codes, in which there is a 1 bit difference, only 1 bit difference from the previous code and in the next code. As you can see over here, this is the gray code of 0 and this is the gray code of 1. We can see bit 0 is as it is, this bit is again as it is, this bit is again as it is, but only this bit, single bit 0 is converted into 1. So there is only 1 bit difference in the bit pattern. So in many application where like example of, if we take the example of soft, moving of soft, so is converted into the decimal code. So it is like rotated by 45 degree, and each 45 degree rotation is represented by one gray code. So the only change when the soft is moving in one direction, the only change in the bit is this only, there is one bit change. Similarly, if we compare the code 1 and code 2, this bit is again same, these two first bits are same, only this 0 is converted into 1. So again there is a 1 bit difference. So in the gray code, as we can see over the complete line, in the previous and in the existing code, there is only a 1 bit difference exists in the gray code. So how we can generate the gray code? So for generating the gray code, let's suppose we have some binary number 0110110. This is in binary, and we want to represent this into the gray. So how we can represent? The first bit is placed as it is over here, and there is a XOR function, XOR gate there exists. So the function of the XOR gate is, if we have input A, input B and output Y, okay, and there is 2-bit input, so the total combination is 1 1. So these are the 4 combination exist for the XOR gate. So for the XOR gate, we have this is equal to 0, this is 1, this is 1 and this is equal to 0. So when there is a different bit, when the input is different, 0 or 1 or 0, we get the 1, or if the bits are same, input bits are same, we get the 0 as the output. So for converting this binary code into the gray code, we use this XOR gate. In this XOR gate, these 2 bits are XOR and represented over here. Like first bit is represent over here as it is. Then we perform the XOR between these 2 bits, that is 1 and 0. Different input, for the different input we have the output 1. So the output is 1. Then XOR is again between 0 and this one. There is again an XOR between 0 and this one, we get again 1, then again between 1 and 1. So these are the same bit, for the same we have 0, then 0, then for different this is 1, again this is difference, this is 1, this again same, this is 0, this again different, this is 1. So this is the gray code representation of the given binary number. Gray code representation of the given binary number. So in this way we can convert each binary number into the corresponding gray code. Similarly, this gray code is again, if we want to, we have the gray code and we want to convert it into the corresponding binary number, we can do this also by converting this gray code into the binary code. As let's suppose again we have this gray code there is exist and we have to convert it to the binary. Then the first bit is again same, and now we have to perform the XOR between the result and the next bit. So the XOR between 1 and 1, for the same 1 and 1 we have 0. Now this result bit 0 is XOR with this next bit, and 0 1 for the different we have 1, for 1 XOR bit with this, for 1 and 0 we have for 1 and 0 we have 1 again, for 1 and 1 same we have 0, for different we have 1, for 1 and 0 we have 1, and for 1 and 1 we have 0. So you can see this is the binary representation of the gray code. And first we take the binary number, then we convert it into the gray, and again we have to again we convert it into the binary. So it must be same, these 2 results must be same. So as we can compare 1 0 1 1 0 1 1 and 0. So same number, same binary number is converted into the gray, and then gray is again converted into the binary, the result is same. So in this way we can perform the base conversion from binary number to gray number and from gray number to binary number as well. Now the next is American Standard ASCII codes, that is American Standard Code for Information Interchange, and these codes are very much familiar to each and everyone, as we can almost daily use these kind of code on our like keyboards. So the printed keys over the keyboard are represented by these ASCII code. ASCII means American Standard Code for Information Interchange. ASCII for information interchange. So the code is fixed. This code is fixed for each and every character, and this is a 7-bit code. Like if we take the example of let's suppose a printing character A, capital A. So for A we have 7-bit, B7, B6, B5, B4, B3, B2 and B1, and for representing A the character is 1, 0, 0, 0, 0 and 1. This is the ASCII representation, ASCII code representation of capital A printing character. So as you can convert it into the decimal number, it is equal to 65. So the code of ASCII code of A is equal to 65, and in binary it is 10000 and 1. In this way, there is a code exists for each, and there is a ASCII code exists for each and every character, like from capital A to capital Z, and from small a to small z, and there is some extra character like asterisk, star, asterisk, star, plus, minus sign. These are again the printing character. There is a fixed code, ASCII code exists, the 7-bit code exists for each these kind of character as well, and for numeric as well, from 0, 1 to 9. So total 94 graphic printing character is available, and there is a fixed code for each and every character. Again, we have 34 non-printing character, that is, these are the character which are not printed over as we press it over the different documents. Like for example, backspace is one of the non-printing character which is not print. When we press the backspace, there is no print, there is nothing print over the screen. So backspace is one example, carrier return is the another example, and many other which is used in flowchart control. Like these are all the, and text, STX, ETX are a non-printing character in the ASCII codes. Then this is the table of the ASCII code for different printing character. This table is very much available on the internet. You can easily find in the many books and internet. So as we can see, we do the example for capital A. So for the capital A, as we can see, bit B7, B6 and B5, 1, 0, 0, and the remaining bit are over this line B4, B3, B2, B1, 0, 0, 0 and 1. 0, 0, 0 and 1. So this is the 7-bit code from B7 to B1 for capital A, as we can see over here. Similarly for E, we have 100 and 0101. So in this way, for small ABCD, full stop, exclamatory sign, brackets, all the printing character, we have different codes, and we can see the codes with the help of this ASCII table. Now next is the error detecting and correcting code. So when we transmit some information over the channel, due to some error like environmental error, or there is some leakage in the data, so due to that error, there is some digital bits that is converted into the another bit. Like if we transmitted some information like 0001 over the channel, but due to some error in the transmission, maybe this 0 is converted into 1 and the rest is same. So how we can find this error and how we can correct? So these error detecting code can help in this kind of detection of error and in the correction of the error. So maybe this one can be converted into 0, or the same, or the rest is same. So the error is of both type. The 1 is converted into 0 as well, and the 0 is converted into 1 as well, as you can see over here. So for this, we have to fix the before the transmission of the ASCII code, we have to fix the parity of the transmission of the transmitting data. And the parity of two type, this is even parity and odd parity, as we can see over here. This is the ASCII character of A, this is the ASCII character of T. So as we can see over here, this is an extra bit which is added to make the parity even or odd. Parity means the number of 1 that is exist in the code. Like we can see over here, for the ASCII code of A, we have 2 1s, which is a even number. So for the even parity, we do not need to add any 1 in the transmission, and we mark it as 0. So it is already even parity number. If we take the example of T, which is having 3 1s, that is its parity is odd. Okay. So for making it even parity, if we are preferring even parity for the transmission, so for making it even parity, we have to add this extra 1 before the code, so that it can be transmitted over the channel with even parity. So now the number of 1 is 0, 1, 2, 3 and 4. Now the number having 3 ones, which is having odd number of ones, but we have converted into the even number of 1 by adding some extra 1 and make it at even parity. Again, for the odd parity, we have to make the number having odd number of 1. So as we can see, the number is even, but we are preferring odd parity. We have to add 1 over here, and similarly for having odd number of 1, we have to add 0, so that number of 1 is odd. Now during the transmission, if any of this bit, like if any of this bit like 0, 1, 0, 0, 0, 0, 0, 1 is converted into some 1, like this 0 is converted into 1. Now we check the parity 1, 2 and 3 and see there is the transmission is even parity, but we get odd, then there is one error in the transmission. So in this way, by checking the number of 1, we can find out the error as well using the error detection in correcting codes. So thank you for this lecture.